fundamental structure on which the entire mathematics language is being written or mathematical science is depicted, and that's the notion of the sets. I'll try to be informal at time, and so as not to lose the essence of what exactly the topic is telling. So we'll basically start with sets, and then we'll move towards pictorial representation of set, which is so called known as Venn diagram. Thereafter, we'll see how two sets can be interacted using something called Cartesian product. And then we'll do a little bit counting of number of sets at the end for the lecture number 1. So all of mathematics can be described with sets. This becomes more and more apparent like the more deeper you go into mathematics. So that becomes more or less like a formal mathematical language. Set is fundamentally is a language in which maybe you can tell is perfectly suited to describe and explain all type of mathematical structures. So let's start with the introduction. So what is set? It's collection of, set is just collection of things. The thing in the collection is known as elements. So we have, let's say, a classroom where we have these students. So we call this collection of a student is a set. So the set of classroom, set of students constitute a classroom, right? So we can have a student, let's say Ram, Syam, Ghanshyam, Mohan, Manmohan, and so on. These objects are known as element of a set. So basically we call Ram is element of this classroom. And so on and so forth. So we are mainly concerned with those sets whose elements are mathematical entities like numbers, functions, like points, and so on and so forth. So basically there is a way in which you describe the sets, and so we describe usually the discrete set with the curly bracket. So this is a fashion in which you describe sets. Suppose if you have to keep one apple, one orange, and one guava here. So how will you put this in a box? It's like set is a collection of objects. So we can put one apple, one orange, and one guava. Now it's important to note, like you can't repeat the objects in the set. So let's say if you have two apples, so that cannot be written as one apple, one orange, or one guava. So this will be a wrong notation. Okay. So the same object should not be repeated twice, more than once. That's how the mathematician has, given the formal way of describing objects in a set. So set will not have repeated elements. So hence 1, 1, 2, and 3. This does not represent a set. Whereas 1, 2, 3, this represents sets because all these three elements are distinct. Similarly, so you are already acquainted with some of the sets. Let's say natural numbers. So set of natural number is usually written as n, which has numbers starting from 1, 2, 3, 4, 5, 6, and so on. So how many elements are there in this set? Infinitely many. We call these objects. The constituents of this set is known as elements of set. Okay, following the usual English temperament. So what will be the set of whole number? It will be the set containing natural number including 0. So we'll have 0 also in the member of the society. So 0, 1, 2, 3, 4, 5, and so on till infinite. Usually to show infinity, like you have an infinite number of objects, we take 3 dots. It's like infinite has no beginning, no end, and no middle, kind of. That might be the philosophy. We can have set of integers, which you do not usually by I, and integers can run from like minus infinity to -5, -4, -3, -2. We have -1, 0, 1, 2, 3, 4, and so on and so forth. So these are sets of integers, right? And more sets. Integer is also written sometimes with capital Z. So okay, you put a bold letter on the inclined part of this Z. So this is written as set of integers. Set need not have just number as the element. You can have even objects like cat and dog in the set. So we have set S, which contains cat and dog. So it's like collection of these two objects, cat and dog, right? It can also be, let's say you have some set B, which can be just T and F, which is collection of true and false. And we use this curly bracket as a fanciful symbol to put the number of discrete items in the sets. Even if they are infinite, still we can use curly bracket. Okay, you can have set consisting of lowercase of alphabet like A, E, I, O, U, these vowels. It's a set of vowels. Even set can also contain sets, right? So even we can have sets which contains, let's say, the vertices of a square. So if I draw the basic Cartesian xy plane, let's say we have this square having point 1 comma 1, it is 1 comma minus 1, it's minus 1 comma 1, we have minus 1 comma minus 1. So I can take D as vertices of this square. So D contains points 1 comma 1, 1 comma minus 1, minus 1 comma 1, and minus 1 comma minus 1. So these are 4 vertices of a square. So that can also be represented as a set, right? Even set can contain sets also, right? So let's say if you have some set E, it might contain a set 1, a number 1, and another set 1 comma 2, or maybe another set 1 2 3, or 1 3. So this itself is a set. So it's like you have a big basket and now you have 3 small baskets inside. Okay, so one basket contains 1. So okay, we have another basket containing 1 2, we have other baskets containing 1 3. Now you see there is a difference between the basket containing 3 baskets and the basket containing 2 baskets. 1 2, 1 3, 1. So what do you feel? Are these two diagrams equal or not? Give a pause and think. Clearly they are not equal, because you can see I've created a basket for 1. So now one can't randomly move anywhere inside this place. So in the second case, 1 is kept in a single box, but in the first case 1 is free to move. So in fact there is a difference in notation. If you try to capture this, you will write it as a set E, let's say containing 1 1 2 and 1 3, whereas the first one will be just written as a set which contains 1 as one of the element, 1 2 as other element, and 1 3 as other element. So I hope you got a difference between these two. So here I can tell 1 is an element of E. So this is again a symbol which I am using, which means belongs to. It's a cool symbol. So this means belongs to. Belongs to. So let's say U belongs to Bangalore. So in entire Bangalore, you are somewhere. Okay, so you are the element in the Bangalore, in the language of mathematics. So in the first case, I can call 1 belongs to E. Let's call this E1 and E2. So 1 belongs to E1, but 1 does not belongs to E2. Why? Because 1 is not a member of set E2. Set 1 is a member of set E2. So in this sense, we can tell like this is basically an element of that set. I hope it is clear. Sometimes we even go with the other notation. So we can have set of even like matrices. Matrices is just collection of, let's say, orange, guava, apple, and banana. So this combination of these 4 fruits together with this big bracket is known as matrices. So every matrices will have some row and some column. So here we can clearly see we have 2 rows and 2 columns. So we can put even numbers in this fanciful structure 1 2 3 4. So where this is a member of first row in first column, this is a member of first row in second column, this is a member of second row first column, and this is second row second column. So even we can have set of matrices. So let's say we have set M. Let's say we have set M, which might contains matrices 0 0 0 0, or maybe 1 0 0 1, maybe 1 0 1 0, and so on. So these 3 matrices are the member of this set. So set M contains these matrices, right? So I can tell like this belongs to set M, this belongs to set M, this belongs to set M, because these are the member of this society. Whereas 1101, that doesn't belongs to set M, because this is not the member of that society. Okay. So now the number of elements which is present in set is known as cardinality of set or size of set. Cardinality is a fanciful name for the size of set. So what is size of set? Number of elements in the set. Number of elements in set. So let's say we have a set of natural numbers. So of course, what will be, how many elements will be there in the natural number set? We'll have infinitely many. So its cardinality is infinite. Let's say we have some set X which contains 1, 2, 3, 5. So what is cardinality? How many elements are there? 1, 2, 3, 4. So I'll tell cardinality of X equals 4. So there is a special symbol for using cardinality. You write in the mod form. So mod X, by definition, we define this symbol as cardinality. Then mod X will be 4. So we have 4 objects or 4 members. Okay. Now there is a special set. Although a small plays a very significant role in mathematical structure, which is known as empty set. So it has nothing in it. So how will you represent empty set? So just will make curly bracket and will not keep anything. You might ask, like, in what sense empty set is useful? So let's say if I give you x square plus 1 equals 0, where x is a real number. So is there any value? Is there any real number x which will make x square plus 1 equals 0? That's not possible. So it has. So for what value of x you will get the answer for this? There is no value of x, right? I'll tell no value of x. So how will you write this in certain notation? S belongs to 5. Okay. So S is empty. Or we can tell like x equals just empty. We can't tell x equals 5 because it means the set contains an object. So this does not mean empty set, right? We don't keep 5 in the empty set. Otherwise the cardinality of set will become 1. Okay, so the empty set means there is no object here. So 5 is equivalent to these symbols, empty set. So you can, if this is confusing, you can just think of a set as a box with things in it. For example, 2, 4, 6, 8 is a box containing 4 numbers. The empty set is an empty box. So it's basically we have a box which doesn't contain anything. If we have some set, let's say 2, 3, 4, it contains 3 objects, 2, 3 and 4. Clear? And you can also note that what will be the number of objects in empty set? So that will be 0. And what's number of object in a set which contains an empty set? So basically, what is the difference between an empty set and a set contains that empty set? Empty set represents empty box, and a set containing empty set means a box inside the empty box, right? It's like an empty box inside empty box. So there is a difference between these two situations. In the first situation, you have nothing inside an empty box. In the second situation, you have got one object which is empty box inside the empty box. So in that sense, cardinality of this will be 1, right? So this is something which is really confusing for most of the kids. So this box analysis will make you think in a nice way. Even we can have set like this. So we can now play a little bit as promised in the beginning. Let's say we have set F which contains empty, an empty set as an object, and some other empty set as an object. So what does this set represent? It may look quite strange, but it's really very simple. Think of it as a box containing 3 things. So we have a big box. So this box represents, the external set notation, which might be represented by this big, giant red guy. And now this contains, so this big box contains nothing. Right? So an empty box and a box containing an empty box and a box containing a box containing empty box. So it's a box. So you can think of it as a box containing 3 things, right? An empty box, and this represents a box containing an empty box, and the third guy is representing a box containing empty box. Okay, so that's the significance of this. So set F is a collection of this entire structure. Okay, so I hope that's very clear. So in that sense, the cardinality of F is definitely 1, 2, 3, because set can contain many sets. In what sense I'm telling? Let's say this is India. So India already contains so many states, plus territories. So this summation, state 1, state 2, state 3, state 4, state 5, say 6, and so on, all these states will sum up to make the entire geographical area of the country. And now again, the states will contain many districts, right? Okay, and so on and so forth. So you can clearly see we have a big set S that contains a smaller sets S1, S2, and so on and so forth. Again, the smaller set can contain still smaller sets and so on, and that will contain still further smaller sets and so on. So set can even contains many sets inside it. Clear? Okay. So now there is a special notation called set builder notation. So there is a special notation called set builder notation, where the name itself suggests you build a set smartly. Set building means you are trying to build a set in a smart way, like it's basically ink or marker conservation technique, or with minimum words how you can replace, which is -6, -4, -2, 0, 2, 4, 6. So this is basically a set notation, right? Can we compress this same information in another fashion? Can it be compressed in that fashion? Yes, clearly you can write the same set Z in a cool way. So I can tell Z is the collection of, again, this box of all the numbers in the fashion 2n. Okay, it's a collection of all the number in the fashion 2n such that n is integer, right? Because if I, let's say, numbers in the form 2n, if I keep n equals 1 by 2, then we'll get 1, it's fine. But if I take n is 1 by 8, we'll get 1 by 4. So that will not give even integers. So Z is a set of even integers, right? Even integers. Now since if you are defining Z as a set of even integers, it's not good to use the symbol Z, right? So that's why, because we reserve Z for integers. So let's call even integers as a set E. Fine. Now again, is there a cool way of writing this information? Yes, you can write set E as set of collection of all those numbers in 2n such that, so this is again a fanciful notation, such that, you can write such that with these double dots or one single dot and one comma, okay, semicolon, such that n belongs to integer. How will you write n belongs to integer? In this fashion. So now we have to speak less, okay, and this notation in a very magical way captures the feeling of all even number, because now you can put as n belongs to Z, so Z itself is a member of society, -2, -1, 0, 1, 2, and so on, -infinity, plus infinity. If I keep n equals -2, we'll get -4, so this member. If I'll keep n as -1, we're getting -2, and 0 will give 0. So each and every member of this set can be got from this definition of set in this cool way. Okay, so we read this like this: the set of all things of the form 2n colon is like such that n is an element of set. The idea is that E consists of all possible values of 2n where n take any value. So in general, if you'll see any set, it will be casted in this fashion. You will have some expression such that some rule of the game, right? Some rule. So this is the basic structure of writing in set. For example, let's say if I take a set of all numbers n such that n is prime number. So now it is set builder form where I'm using less word, and if you want to write in another fashion, like personalized attention, if you want to give so 2, 3, 5, 7, 11, 13, 17, 19, and so on and so forth. Okay, we can define a new set, let's say n square, such that n belongs to integer. So how this will decode to? It is same as telling if n is 0, because the integer world is -1, 0, 1, 2, 3, 4 infinite, similarly -2, -3 and so on. So this set will start from now 0 now, 1, 4, 9, 16, 25. So it's a collection of all numbers which is perfect square, right? Let's take few more examples. Let's say we have a set X, collection of all object X belonging to real number, such that x square minus 2 equals 0. So what element is there present in this set? Clearly it has got two elements, x equals √2 and minus √2, because if you solve this, x square equals 2 implies x equals plus minus √2. So both these elements is a real quantity. So this expression follows that rule of the game. In the same question, if I give you x belongs to integer such that x square minus 2 is 0, then that will represent an empty set. Very good. So this is going to represent an empty set because there is no value of integer whose square is going to be 2. So x square equal to 2 cannot happen for integer. It will happen for irrational number plus minus √2. Let's say if you have some more example, x belongs to integer such that magnitude of 2x is less than 4. What does it mean? Mod of 2x. Mod means the absolute value. So mod of minus 2 is 2, mod of 2 is definitely 2, mod of 0 is 1. So mod is like of negative or positive, whatever quantity you give, it will just give you absolute value, which is just cube, right? So if 2x is less than 4 and there is integer, you can try, x0 will work, x1 will make 2 less than 4, so x1 works, x2 is not working, right? Because 4 less than 4 is wrong statement. x3, 6 less than 4 is definitely wrong. So now you can't go further in this direction. X equals minus 1. Yeah, it's working because 2 is less than 4 is fine. X equals minus 2 is not working because minus 4 mod is less than 4 will imply 4 is less than 4, which is clearly wrong. So these examples highlight the conflict of notation that we must always be alert to. The expression mod x means absolute value of x. In the cardinality, it represents if it is a set, right? So this distinction should be very clear from the context. For example, suppose if I give you x belongs to z such that mod x less than 4, right? So here x belongs to z, so x is a number, not a set. So clearly here x is a number which belongs to this integer. So it's not a set. That makes sense? So x, like can take a value of minus 3, minus 2, minus 1, 0, 1, 2, 3. All the value will work for this. So thus the bar in mod x must mean absolute value, not cardinality. On the other end, suppose if I have A equals a set containing 1, 2, and set containing other set 3, 4, 5, 6, and let's say 7. And let's say we define B as all that set X which belongs to this set A such that mod X is less than 3. So now can you decode this question? What does it mean? So read the question again. Set A contains 3 objects. So set A is basically a bigger box that contains 3 boxes. One containing 7, other containing 1, 2, another containing 3, 4, 5, 6. Now what does B represents? B represent a set X which belongs to A. Okay, so A itself is a set. So in any element of the set will be either. So this set A will have just 3 elements. Either it is this box or this box or this box. So X can take only 3 value. X belongs to A means X is a member of this box. So inside this box we have 3 other boxes. So X can be either 1, 2 because X represents set, right? Or X can be 3, 4, 5, 6 or X is 7. Now here mod X definitely represents cardinality because we are talking about set. So here mod of 1 comma 2 does not mean absolute value, right? Clearly it means cardinality by default by the context of the problem. So how many set X has cardinality less than 3? This has cardinality 2, this has got cardinality 4, this has got cardinality 1. So this answer set B contains 2 objects, right? So I hope the context in which you are doing the questions will make it very clear. So if someone wants to write B in other form, so the only allowed candidate in set B is going to be 7 because cardinality is less than 3 or 1 and 2. One thing worth noting, like it doesn't matter in what form you put the elements, whether you write AB or BA, it represents the same set. Okay. So two sets are equal if their cardinality is same and the objects inside the box is same. It doesn't matter in what order you put them, because let's say if you have a box containing one chocolate and one ice cream, and you have other box containing one ice cream, one chocolate, it's basically same because you don't know like what they are doing inside. Okay, so it's basically that represents same set. So we close this session, which is summary of special sets. So these sets are types of set that comes so often that we give a special name or symbol to this, as we have seen before. So we call empty set as empty. This is first notation. And then we have used the set of natural numbers, which is 1, 2, 3, 4, 5 and so on. We have set of integers, which starts from minus infinity all the way to minus 3, minus 2, minus 1, 0, 1, 2 and so on. We define set of rational numbers, and all of you know the definition of rational numbers is all those numbers x such that x can be written in the form of m by n or p by q, where m and n is integer, and there was more condition, n is not equal to 0. So you can't allow the denominator of a rational number for so reason for any number 0. Let's see like why we can't allow 0. So suppose if you have 1 by 0. So usually in textbook you'll see like division by 0 is not allowed. Division is not allowed. So now the question is why 1 by 0 is not defined. So let's think of division. If I ask 4 by 2, you know the answer is 2, but why? It simply means how many times you are adding 2 to get 4. So we take 2, how many copies you need to add to get 4? It's 2 copies, right? If I ask the question 4 by half, how many copies of half you need to create 4? So half, 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 half. If I add them, I'm still at 2. So we need 4 more copies, right? So you need 8 copies of half to get 4. So hence 4 by half becomes 8, and then you come with the rituals of flipping and all that. Right? Now ask the same question. If I ask you what about 4 by 0.0001? So how many copy of 0.0001 you need to create? So this is too small, right? So of course there will be many copies, right? Many copies. But what exactly will be the answer? You know what will be going to be? 40,000. Okay, so many copies we need to take. What will happen if this becomes more small? So 4 by 2 small, or for the same reason, so it's becoming too big. Okay, so when 1 by something which is almost in ICU will go to Mount Everest, right? It will go to infinity, and this is a symbol for infinity, which has no meaning. Sorry, it has. So this is a symbol for infinity, which has no beginning, no end, and no middle. So these are, now I'll give you some more special notation, which is fun doing this. And to understand this notation, before we go, so with this idea, you know, like 1 by 0 is fundamentally asking you how many times you'll add 0 to get 1. So no matter, it doesn't matter how many times you add 0. You add 2 times, you get 0. You add 3 times, you are still 0, and you get frustrated. It's basically out of nothing, you are trying to create something. And it's violation of law of conservation of mass or energy. So basically violation of first law of thermodynamics. Hence we are bound to make it not defined. So So if you forcibly wants to define it to be some number x, and x into 0 is 1, so which gives 0 equals 1, which is an inconsistency. But this proof has a flaw in it, because from which step you got this? Okay, to go from this step to this step, we have used the property is like multiplying y0, max 0 y0 as 1. Okay, so if I assume 0 y0 1, then I can write x into 0 equal to 1. But this assumption itself is a flawless assumption, because out of nothing, what about 0 y0? Out of nothing, you're trying to create nothing. So it can be everything, because now you apply the same logic. How many times you need to add 0 to get 0? Now it's universal truth. Whether you add 1 times, or you don't add it at all, or you add only 24 times, it will always give you 0. So this can take value of 1, 2, 3, 20, 24 and everything, because out of nothing, trying to create nothing is a universal truth. So mathematics is greeting you. Right? In calculus, often we use some more notation. So let me talk about some more notation. Let's say if you have wall 1 and wall 2. So now what are the possibilities for you, like to connect a strings to this wall? Maybe like both wall, in the limiting case, I can travel from here to here. So this is my degree of freedom, so that I will not touch either wall. Or maybe I'll not touch the left wall and I'll touch the right wall. Or I'll touch the left wall and I'll not touch the right wall. Okay. Another journey can be I'll touch the both wall, right? Or maybe you are so powerful that you'll touch this wall and you'll break the other wall. Or other way around, I'll touch the right wall, I'll break other wall. Or it might happen you're so powerful like you're going to break both the wall, right? So if you break both the wall. Okay? Still, is there any more case left? Yes. So let me first make wall more longer. We might happen like I'm not touching the left wall, but I'm breaking the right wall. Or I'm not touching the right wall, but I'm breaking the left wall. Okay, so crossing it. So crossing the wall means breaking it. Now in calculus, all these situations. So we have situation 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we have one, of course, the most powerful situation when you break the both wall, right? So this is a situation when you're breaking both walls. So let's try to depict this in a mathematical way. I mean like set notation. So let's call it this represents wall A and this represents wall B. So I'm allowed to take up any values between A and B, right? So let me take a specific particular example. Let's say this point represents point 1 and point 2. So you are on a number line and this represents 1 and 2. So 1 is like left wall and 2 is right wall. So how many positions are there between left and right wall? There are infinitely many positions. We can have 1.1, 1.2, okay, 1.2, 1, 0, 0, 5, 2, 1, something like this. Even you have root 2 also, irrational numbers, right? We can have 51 by 2024 and so on and so forth. So there are infinitely many points between them, infinitely many points. How will you write the first answer? So very cool way of writing the first answer, as obviously you can see, is we are not allowed to touch the left wall, neither we are allowed to touch the right wall. So we write this with a small bracket when you are not touching. Okay, so with a small bracket signifies that you are not touching the wall. So 1, 2. This is a small bracket 1, 2 represents. It not only contains two objects 1 and 2, but it contains infinitely many objects between 1 and 2. So 1, 2 represents, it also represents all the continuous number between 1 and 2. So 1.1, 1.2, 1.3, 1.4 till 1.99999. So all these numbers represent here. So it's like continuous interval. For the second one, 1 is not included, but 2 is included. So when you include a wall, you use this big bracket. Kind of is trying to capture this. Okay. So when you have to exclude, you use this small brackets this way or that way. When you have to exclude, use this small bracket, include, use this big bracket. So for the second case, what will be happening for the third case? Now including first one, but excluding 2. Fourth case, we are including both 1 and 2. Fifth case is interesting. You are including 1, but you are breaking the wall. So if you break the wall, where you are going? Till infinite. So can we include infinity? Of course no. Why? Because infinity is something which you cannot trap, which you cannot capture. Otherwise the question will be what next? So hence infinity is always excluded. What about this guy? It starts from minus infinity. Of course you don't know what's beyond minus infinity, so excluded until 2. What about this guy? When you are breaking both wall, minus infinity to infinity. What about this? We are excluding 1 and going to infinity. We are excluding minus infinity and going to 2, and this we have already seen, minus infinity. So this is the very, like a pictorially, what does including excluding mean just with one diagram, right? So in general I can tell x belongs to a comma b. What it means? It's equivalent to telling we have a number a and b, and now you can pick up any continuous value between a and b. So a is allowed, b is allowed, and any point between a and b, infinitely many points is allowed. Instead, if someone tells you x belongs to curly bracket a and b, so it means you have just 2 objects in the box, a and b, nothing else. So this box contains infinitely many objects, and all objects can come from here. But this box in the second case contains only 2 objects. So that's the difference between these notations. Sometimes the open bracket a and b is also written in a fanciful form. It's like you are not capturing a and b, okay? So I feel like it's not a good way of writing, but I still like in some textbook you'll see this. Because if this is meant for capturing Golu, then this is meant for like relaxing Golu. So usually when you solve the equations, you write in this form. Yes, clearly we can also put this other symbol. Let's say if you have a to infinite. So this can be written as a set containing all x belonging to real number such that x is more than equal to a, right? So all real number a, what it means, like it starts from a and you can take up any value till infinity. So this is still an equivalent code symbol for this. In the next lecture, I'm going to give you the brief idea of Cartesian product.